Now let's consider Ampere's law in this video. Now consider an infinitely long wire in which current flows through the wire this way. Now remember our right hand rule. Whenever current flows this way and I place my thumb like this towards the direction of the current, then know that the magnetic field will move along this direction. We know that already. Now, according to Ampere's law, you see, for you to solve Ampere's law, this law relates magnetic field and electric current together, but it is around a closed loop like this. Altogether, it relates what? Magnetic field and what? Current around a closed loop. Now, you see this loop I'm drawing here like this, we call it the Amperian loop. And what happens, according to what Ampere's law, the line integral along this closed surface of the magnetic field dot dl is equal to what? Mu naught times what? The current enclosed by that loop. That's what Ampere's law. So I can say that what Ampere's law relates the magnetic field around a closed loop and the electric current enclosed by that loop. Again, Ampere's law relates the magnetic field around a closed loop called the Amperian loop and the electric current enclosed by that loop. Now, let us now find the magnetic what? Field outside a wire, and we'll consider another one inside the wire. Let's go. Now, consider this wire this way. I want to draw it in a way that I want to consider it from the top like this. Now, look at this. The current shows that this current is coming what? Outward. And remember, if it's coming outward, if I place my thumb like this, then the magnetic field is around what? This direction like this. Now, if I want to find the magnetic field outside this wire, what happens? What I'm going to do is that what? I will draw a closed loop. Remember, Ampere's law, I will draw a closed loop. This loop is called the Amperian loop. And let me say, remember, from here to here is the radius of the wire. Why from here to here like this is the what? Is the radius of the what? Of the Amperian loop. Now, according to this Ampere's law, the line integral along this closed surface of B dot dl is equals to what? Mu naught times what? Times the current what? Enclosed by this Amperian loop. Now, note that this B and this dl, they are always what? Parallel, pointing in the same direction. You can see pointing in the what? The same direction. So that shows that what? The dot product will just simply give me B dl. So I have the loop to be what? B dl equals to what? Mu naught I what? I enclosed. Now from here, you observe something that this one is now a constant, so I can bring it out. dl equal what? Mu naught I what? Enclosed. Now from here, what will I do? Remember, if I want to sum up the total length like this dl, if I want to sum, you can see that what this dl is traveling like around a circle, right? So it means that what this dl, I'll actually use the circumference of the what? Of a circle. If I sum up this dl at each of these points, you see that what? I'm summing up the circumference of the circle. So this one will be times 2 pi r equal mu naught I enclosed, and that's it. So from there, B will be equal to what? Mu naught I enclosed all over 2 pi r. And this is the formula to find the magnetic field outside a wire using the Ampere's law. And remember that for Ampere's law, we always consider a loop. It must be what? A closed loop. So it means that what? This magnetic field depends on the amount of current entering what? Entering that loop. Okay, so that's that for that.